Okay, we begin by reminding you what we went over last week. So we started discussing, like more analytic things, really. I mean, just as we went over the motivations for studying sequences, and we actually gave the definition, the rigorous definition of a limit, and how you have to prove the things converge to an supposed limit L. So this the sequence is converges to L, then something must be true, and that is it for every epsilon. So sequence. So remember, if we had a sequence AN, right? Is said to converge to L as n goes to infinity if, and this is the statement that you should memorize or internalize. You should understand, so it's not just memorizing it. So for every epsilon greater than 0, there is some some capital N in N, such that for all n greater than or equal to that n, a sub n minus L is less than epsilon in absolute value. So this is what it means for a sequence to converge to a limit L. And so this is the definition that we're going to be using from now on. Also, when we talk about a series, which is the main application we have in mind right now. Okay, so when a sequence, so this is also a definition here, no definition in the book. I mean, well, though it's just a notion, the natural notion to have for a divergent sequence. Oh yeah, let me see what is the number of this definition 2.2.9 if you want to look at it in the book, although just not much information here. So a sequence that does not converge, meaning there's no L such that the above statement is true, is said to be divergent. So that's a very important thing. So if you try for every single L, I mean, this is just a way of way of saying it. I mean, a way of presenting it, so that you can actually go and try every single L. But if there's no L in R that will make this statement here true, then the sequence doesn't converge, or what is the same, we say that it diverges. Now, what is a very important thing about limits, a very important property about limits is and see here in the book we have theorem 2.2.7, which is referred to as the uniqueness of limits. They phrase it like this. So the limit the limit of a sequence when it exists must be unique. Okay, so if, of course, I mean the statement doesn't make sense when a sequence doesn't converge, but the point here is that it it's I mean you can actually say that there's you can speak about the limit and not a limit for a sequence. So a sequence has I mean it may diverge, or if not, it has a limit. So one limit, and that's the limit of the sequence. So it is correct to talk about just the limit of a sequence when that exists. You don't get to have multiple multiple choices for a limit. I mean that actually happens in more general topologies. In fact, a sequence may converge to every single point. But here in the topology we're considering here on R, there's only one possibility for a limit. So either it has one limit or no limit at all. There are no more options. Here this is left as an exercise, but we'll do it here in class, just so you get used to proving statements like this. The idea here, so the picture proof first, let me do it somewhere over here, is that if you have, say, two limits, L1 and L2, so here's the real line, a sequence xn cannot be eventually very close to L1 and L2 at the same time, because if you let us say L1 plus epsilon, L1 minus epsilon, you make a very small epsilon. Oh, this is L2 minus epsilon. This is L2 plus epsilon. Then the whole sequence, what this statement here, this statement here is telling us is that eventually all of the sequence is contained within an epsilon neighborhood of L, the limit. And so if that is the case, then eventually all of the elements of the sequence will be contained within this neighborhood, but also in this neighborhood at the same time. And that's impossible, right? Because those two, I mean, being in two sets would mean that these two sets would have to intersect. But by choosing epsilon small enough, you can see that that's not possible. I mean, if L1 and L2 are both, I mean, if L1 and L2 are two different numbers, L2 is greater than L1, say, then if you make epsilon small enough, these two neighborhoods are going to be disjoint, and therefore the sequence cannot be, an element cannot be in both of these neighborhoods of L1 and L2 at the same time. So in this small intervals L1 minus epsilon, comma L1 plus epsilon, and L2 minus epsilon, comma L2 plus epsilon. So that's the idea behind the proof. So what we're gonna do? So to let L1, L2 be limits for an, so for a sequence. Here I'm not actually saying, I mean, I'm not saying that the L1 and L2 are necessarily different. I'm just saying that there are two limits. Maybe they're the same. In fact, that's what we want to show. There are two limits for an. As, of course, as n goes to infinity, So n goes to infinity. Okay, so we know that if L2 is not equal to L1, this is the part where we're just saying something. Well, L2 is not equal to L1. Well, we're actually asking them to be different, otherwise there's nothing to show, and we want to show that they're the same. Then, yeah, we're just now assuming that L1 and L2 are not equal. Then L2, I mean, without loss of generality, we can assume then we can assume that L2 is greater than L1, which implies, I mean, this is just a trivial consequence, but so it implies that L2 minus L1 is some is equal to some 2 epsilon, say, so, which is greater than 0. So their difference over 2 is going to be some number that is going to be greater than 0. In fact, I'm going to keep this statement not in parentheses. This symbol here means therefore. Okay, just so you know, but I'm just going to write it. Therefore, this number epsilon, it's going to be greater than 0. Right? So, how do we use this? And remember the picture that we drew just a little while ago. I mean, some minute ago or so. What's the idea? I mean, we have an epsilon that is greater than 0, and we know that for that epsilon, I mean, if L1 and 2 are both limits for the sequence, then this statement must be true for both of them. So for that particular epsilon, it holds for all epsilon, in particular for that one. So there must exist an n so we okay, so these are the facts that we know. So there is some n1. The n's need not be the same. I mean, the statement just tells you there's one n associated for each possible limit, such that for all n greater than or equal to n1, an minus L1 is going to be less than epsilon. And the same thing holds for the other limit in principle. For all n greater than or equal to n2, some n2, which is associated to the other limit, an minus L2 is less than epsilon in absolute value. Okay. So then, what is the problem here with these two statements? If you remember the drawing, to the distance, L1 minus L2, or L2 minus L1, it's the same thing. I mean, they're absolute value, but since we already defined, so this is going to be equal to 2 epsilon. So we already defined epsilon up here. We're going to use that. I mean, it's the difference between L2 and L1 divided by 2. So this means that this is equal to 2 epsilon. Remember, L2 is greater than L1. Therefore, this absolute value is just what's inside. So L2 minus L1. By the triangle inequality, this is less than or equal to L2 minus AN plus AN minus L1, which is going to be less. This is going to be strictly less than epsilon for the first one if n is greater than or equal to n2, right? Because of this property. And the second term here is going to be less than epsilon 2 if n is greater than n1, greater than or equal to n1. And this is equal to 2 epsilon. So 2 epsilon seems here that is, well, is equal to that, is less than or equal to that, is less than 2 epsilon. This is just equal to that, but this expression here is greater than everything that appeared before in the same line. So 2 epsilon is less than 2 epsilon, and that's not possible, so that's a contradiction. Because we can always find a number that is greater than both n1 and n2 at the same time. You pick the maximum, and if you use that n, then you will reach a contradiction. So that means that, I mean, what is the thing that we assume here that was not true? Was that L2 was not equal to L1? Because that allows us to say, well, if L2 is greater than L1, if L2 is greater than L1, then L2 minus L1 half will have to be a positive number. Of course, the same epsilon here is defined is not a positive number, it's just 0. So that's the contradiction. So that's the uniqueness of limits property. So you have a bunch of problems I'm going to give you that I want you to work on. But so now I will just go ahead and move on to section 2.3. The algebraic and order limit theorems. Let's write it off. So these are the common properties you know about limits from Calc 1. You use them many times. Multiplication by a constant, adding limits, and so forth. You know, these kinds of things. The only thing we're doing now is making all this. Improving everything. So doing the analysis in a rigorous way. So what's the definition here? The first definition here is definition 2.3.1. Just write like this. Definition 2.3.1. This is a preliminary step to the properties that we want to show. I mean, here, the main point, as we said, is to go over the properties you know. I mean, if you multiply a constant times a sequence, and the limit of that sequence will be constant times the limit of the original sequence. If you have you have two sequences, an and bn, converting to say limit L1 and L2 respectively. I mean, so sequence an converting to L1 and sequence bn converting to L2. Then if you add them create a new sequence, so an plus bn, then this sequence will converge to a L1 plus L2, as you would expect. These rules alone are not going to be enough for us, and the rest of the section of the chapter, I don't remember well. It's about, putting everything together. This is going to allow us to produce new limits once we've shown that a given sequence converges, or a set of sequences that converge. But we need to be able to prove that these some initial sequences converge. So some we'll be able to find explicitly, some we will be able to obtain by using these algebraic and ordered limit theorems. So at least some properties about them. The ordered limit theorems are not really about obtaining limits, but obtaining some bounds on the possible limits that you can obtain for certain sequences. But in order to say that that a certain sequence converges when you don't know the limit, we need to resort to the least upper bound property. This is something I mentioned last week. So this is a very important property. If the sequence is bounded from above and is non-decreasing, then the sequence is convergent. This is just based on the least upper bound property, and this is something that we need. But we also see that every bounded sequence has a convergent subsequence. We'll see what subsequences are in a little while. But for now, in order to discuss all these things, we need to introduce the notion of boundedness for a sequence. So a sequence xn is bounded if there exists a number m greater than 0 such that xn in absolute value is less than m for every n in n. So if there's a number independent of n, such that all the elements in the sequence are less than that given number, in this case m, in absolute value, so this is what it says in here, so the xn in absolute value are all less than or equal to m for every n, and that property is true for every n in n, then the sequence is bounded. And so the first thing you want to show with respect to this is that, of course, if a sequence is convergent, it's going to be eventually close to the limit, and actually as close as you want. Just need to just need to choose perhaps larger and larger n's in the definition of convergence. But then that means that it's going to be the tail of the sequence is going to be bounded. But what's left? Well, it's not the tail of the sequence. They're going to be finitely many terms, right? And of course, a finite set is always bounded. And then you consider this the tail part, which is going to be bounded because it's going to be trapped in a small. So all the elements in the tail are going to be within an epsilon neighborhood of the limit. Then you can see by putting these two things together, you're going to see that the whole sequence is bounded. Okay, so this is the idea. So every convergent sequence is bounded, as you would expect. Okay, so then proof of that fact. Let me see. So here we conclude the proof up here. Proof. Let xn be a sequence and L its limit. Right, so we have a convergent sequence and we call its limit L. We know that for every epsilon we can find an n, blah blah blah. So that, but in particular for epsilon equals 1, there exists, let me just use it, this is there, n in n, such that for all n, same thing, for all n greater than or equal to n, what do we have? Xn minus L is less than 1. Remember the statement for convergence tells you that for every epsilon something happens. In particular, it should happen, if it happens for all epsilon, it should happen for epsilon equals 1. So there must be an n that depends on the epsilon, in this case 1, so n sub 1 if you will, since epsilon equals 1, whatever you want to call it, such that for any value of n greater than or equal to n, the distance between xn and L in absolute value is less than 1. 1 here because 1 is epsilon. We chosen epsilon equals 1/2, this would be less than 1/2. So then that means that here, this means that xn minus L has to be greater than -1 and greater than, no, and smaller than 1. If it's smaller than 1 in absolute value, it has to be a number in the interval -1 and 1. Otherwise, we'd have an absolute value greater than 1. If it's -2, say, its absolute value is 2. So the values of xn minus L lie between -1 and 1. Again, just because of this property here. So the distance between xn and L in absolute value is less than 1. I mean, the distance between the two is less than 1. So the absolute value of xn minus L is less than 1. So this statement here is completely equivalent. This last statement is equivalent to saying that L minus 1 is less than xn is less than L plus 1. And this means that, well, I mean, this is clearly greater than, we don't know, of course, if L is negative or positive, so we know for sure this is greater than or equal to minus the absolute value of L minus 1. Minus 1 is just minus 1. And L, if it's positive, is most certainly greater than the absolute value of L minus the absolute value of L. If it's negative, it's actually equal to that. And we can do the same thing here. So this is less than or equal to, on the other side, on the other end, xn is going to be less than the absolute value of L plus 1. This is going to be equal to L when the absolute value of L is when L is positive. But these two things put together, this is just minus the other one. So this is equivalent to saying xn is less than or equal to the absolute value of L plus 1 in absolute value. But since the absolute value of L and 1 are both positive, and you're adding them, this is just the absolute value of L plus 1. Okay, so you're just saying that this is less than or equal to that. So xn is bounded in absolute value for all values of n greater than or equal to n. N is fixed here, so we just picked one epsilon. Epsilon equals 1. So there's only one capital N here. So if we choosing M to be the maximum between the absolute value of x1, the absolute value of x2, to the maximum, the absolute value of xn minus 1 of n minus 1, comma, the absolute value of L plus, absolute value of L plus 1, we have the property right. So all of the elements in the tail are gonna be less than the absolute value of L plus 1. So beyond n, all the elements in the sequence are gonna be bounded by the absolute value of L plus 1. And before, each one of those numbers are going to be bounded with one of these. So of course, if you pick the maximum among all of these numbers, these n numbers, then all the sequence is going to be bounded by this bigger, perhaps bigger number than perhaps bigger number than the absolute value of L plus 1. Okay, so that's how that's how we show that if you have a convergent sequence, then it must be bounded. And notice here, of course, that if the n, the capital N you end up with, happens to be equal to 1, there are no terms in here. So just the absolute value of L plus 1. So that's just so x minus 1 doesn't exist. X of n minus 1 doesn't exist. This is just notation for the general case when n is actually greater than 1. Capital N is greater than 1. So we have the property, which is what we wanted to show, and this is the end of the proof. Then the next thing we're going to do is going to go over the algebraic limit theorems. We're just going to prove one statement, and then we're going to leave the rest as exercises, and we're going to keep going with the material. Okay, so just just wait for the next video and study it thoroughly. I mean, just to make sure that you can do stuff on your own. I would recommend you to try to redo these proofs on your own, and that would be a good practice. And then check with the proof that you're actually getting the right, you're doing all the right things. And as a general advice, I mean, don't try to cheat yourself and start looking in the middle. Try to prove everything from scratch after watching the video, and if you can do that, then you're in a good you're in a good position to keep going with the material. You have any doubt, then you can look a little bit, but try to just look enough to get unstuck, but not to see the whole proof. Okay, but the ideas, I mean, if you memorize the ideas, you will be able to reconstruct these proofs in the future. Okay, so that's the most important thing now. So just try to, I mean, this kind of arguments are gonna be present in everything we're gonna do from now on. So I would recommend you to just try to perform these proofs on your own, and then checking if you got every step right and the right order, and you proceeded as I did here. I mean, for the most part. Okay, so then after we, as I said, we go over the algebraic limits, which is what we're gonna do next. We prove the most important property, the fact that well, I mean, there's some small stuff for just saying some elementary properties called the order limit theorem, or all in the order limit theorem, all these basic properties. Like for instance, if a sequence is non-negative, then of course the limit cannot be negative, and stuff like that. And then the things that are going to be very important to us are going to be the fact that every non-decreasing and bounded sequence is going to be convergent, which is called the monotone convergence theorem. And then the fact that once we talked about subsequences, the fact that every bounded sequence has a convergent subsequence. So every bounded sequence has a convergent subsequence. And once we do that, then we'll start doing more stuff with sequences, which is something very, 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 very important. Because everything else, I mean, even when we deal with functions, there are going to be sequences of functions that we need to work with, and there are going to be sequences of functions, so we need to still talk about convergence. But the ideas, as for instance, like the triangle, the use of the triangle inequality, and things like that are going to be present every single time. And I mean, you have to become comfortable, using the definitions to prove stuff. So that's part of the reason why I'm going to ask you this week I'm going to give you the opportunity to work on something plus extra credits on Thursday. And if you do well, of course, very good for you, and you're going to be very well prepared for the exam. If not, then that's going to give you an idea of what you should expect for the exam, for the next midterm. Okay, so that's it. See you in the next video.